Okay, hi everybody. Would you please turn on your camera? So I can see you guys. May I ask others also turn on the camera so we can start? Thank you guys. Okay, let's start. But before we jump into the detail, hopefully you got my message over Piazza about the next quiz. It's very simple. I just wanted to check that you're following the lectures stuff. It's mostly about performance that we talked about several times, trade-off. That is a free-form kind of questions. Try to provide a reasonable analytical answer. So I can understand what you're saying, and hopefully I presume all of you should be able to get the full score for this. It's very simple. And we'll go over it. We discuss it next week once you submit your solutions. Is there any question about anything before we start? Nothing?
What exactly is the quiz on?
Did you see it? Did you check the grade scope?
I'll check it right now.
Yeah, it's about performance. The questions are clear, but if not, feel free to discuss it over Piazza in a public forum so others can help. But it should be very clear if you have followed the lectures.
Thank you.
Sure. Okay, we'll continue. Microarchitecture. We somehow discussed the basic concepts and building blocks previously in the last two lectures, specifically whatever you need to know in order to go ahead and somehow build a single cycle microarchitecture. This is what we'll discuss today. And as I mentioned, before we start with a simple instruction, one type of instructions, and then as we progress, we add more instructions. So this microarchitecture becomes more complex by adding more building blocks, more logic gates in order to implement the instruction appropriately. So it's mostly about wiring things and sending the right. So it's microarchitecture is very simple, like building data paths in order to move the data to the location that is needed, and also sending the right control signal. Is nothing more than that. So remember, may seem complicated, but it's not really. So constructing the right data path to move the data and sending the right control signal. That's it. So somehow it's simple once you grasp the notion. And we discussed this simple 5 or in some versions 6 steps: instruction fetching, instruction decoding, and and evaluating the memory address, memory operand fetch, basically whatever we need to fetch from the memory, and storing back result. This storing could be in terms of mostly storing the stuff in registers, but sometimes inside the memory address as well, right, depending on the instruction. So these are 5 or 6, depending on how you interpret it, of the steps that every single instruction needs to go through. And previously we discussed that, okay, these are like generic. Some instruction may not need a particular step of one of these steps, right? So we discussed this when we started talking about assembly, MIPS assembly, essentially, several lectures ago. For example, like a very simple example, some instruction do not write into the memory, right? So this storing back to the memory is not happening, right? So some of these steps is not happening in some instruction, but these are the generic steps for each single instruction. And this is the full macroarchitecture. By the end of this lecture, we'll get somehow into the full macroarchitecture. Again, this makes things complicated, but as we will build, this is another version, but both of them referring to the same macroarchitecture, right? With few some minor differences. And as you know, you could have multiple implementation of the same ISA, so multiple macroarchitecture. Some of them are minor, they have minor differences between each other. Some of them vastly different, depending on the objective performance trade-off. Okay, so let's jump into the interesting part of this. And we start by R-type ALU instructions. These are somehow essential, important type of instructions. One category out of few others, category of MIPS instruction or general assembly instructions. Hopefully you remember what I'm talking about. Beyond R-type, we have I-type, we have like memory access, memory movement, data movement types, right? So we have different type of instructions. So we start constructing this single cycle macroarchitecture for MIPS by R-type, and then we add more types of instruction as we move forward. Okay, so for example, add, is an R-type instruction. It expects 3 registers, right? So S0 is a destination register. S1 and S2 are the source and are the source registers that basically you add S1 to S2 and you store it in S0. So you know how to interpret this assembly, right? So you hopefully remember the encoding of this type. So this encoding is shared among other R types. So this first 6 bits are 0. These 6 bits at the right side are encoding the type of function, right? And the other bits, as you see here, specifying what is the destination register, what is the source, and what is the target registers. And here is how the semantic of this instruction has specified. Very clear. So if memory address of the PC is equal to this instruction, meaning the add instruction, you need to add the content of source register, whatever value that resides in the source register, add it to a target register, and once you add them up, you put it into the destination, and you increment PC by 4. Okay, very simple semantic. Hopefully it is super clear for you. And please, if you need any clarification, like, please ask. I don't want really some of you sending me like, we cannot follow. If you cannot follow, please do ask. Do ask it here. I can explain in other way. I can clarify everything for you. But if you don't ask, I cannot help it. Ask, no shame in asking.
I have a question.
Yeah, go ahead.
So at the bottom, the PC to PC plus 4, what is the significance of the adding 4?
Meaning that the PC should, you remember, the PC should move to the next instruction. You remember this had two parts. So beside executing the current instruction that is pointed by PC before incrementing it, right? So PC every time points to the instruction that the machine should execute, right? So you should at the same time execute this instruction, also increment the PC, so next time you execute the next instruction in the code, right? So your and you know that the machines, when Newman machines, you store the instructions into memory in addition to data that you store. So both instruction and data are stored in the memory. The second principle, the second property is that instruction should get executed one at a time, right? This makes sure that you execute the instruction sequentially.
Okay, so it's like a pointer adjustment?
Yes, exactly.
Okay, cool. Thank you.
Sure. And by 4, you remember, like, MIPS is byte addressable. So you need to, and each word is constructed by 4 bytes. So you need to add 4 instead of 1. If it were word addressable, you only needed to add 1. But MIPS is byte addressable, so you need to increment it by 4 to point to the next word in the memory address. And hopefully it is clear, right? So this is the semantic of add. And the only thing in order to build a microarchitecture at a high level is meaning that you need to translate the semantic of each instruction into combinational state update logic, right? At the abstract level, you remember, you need to transform the architecture state of the system from AS to AS prime, okay? And architecture state of the system you remember what are the states? Like you had register files, you had PC, right? You had let me go back to this important slide. Where it is here, right? So these are 4 building blocks or state elements of a microarchitecture: PC, instruction memory, data memory, both instruction memory and data memory referring to the memory, but is separated for some purposes because you access it at different steps, right? And also register files. So you definitely need to have these state elements, right? What you need is to have some combinational logic in order to make this transformation from AS to AS prime. So we need some sort of logic gates, combinational logic, in order to make this transformation happen. So this is at the abstract level. When you are going to implement it, so this is the detail, right? Let me explain it. What you see here, the interpretation is important. Once you are able to interpret this, then obviously you can build this as well. So here, obviously we need PC. This is again the first step. You need to know. You need to locate the instruction by PC, okay? And you already know that you should increment the PC by 4, okay? So let's focus on this part. So you need definitely an adder. Adder is again a logic gates that you give 2 numbers. It adds them up together, right? So in this case, you need one number coming out of the PC, and the other one is static 4. You always need to add 4 to it most of the time, but you already should guess that sometimes you may need to add different numbers. We will get there when we will discuss about jump, right? But for now, by default, we add 4 to PC, and the result will be wired back to PC, will be written back to PC. Okay, so hopefully this part is clear. Let's go to the other part. Here, you need to read the address. This is again memory, instruction memory. You need to read the address, fetch the instruction, okay? An instruction tell you what is the encoding, okay? So again, go back to this encoding. You know from what are like exactly from bit number 0 to bit number 31, how you need to locate, how you need to retrieve each bits and pieces. And here, like how many pieces you have? 1, 2, 3, 4, 5, 6. This 6-bit and these 5 bits, you are not going to use them, at least in add, right? In R type. But the other part, these 6 bits, these 5 bits, these 5 bits, these 5 bits, are going to be used at the microarchitecture in order to implement this semantic, okay? Because you need to know once you retrieve this. So here, you retrieve 32 bits, okay? Here you exactly, you have 32 bits. Then you need to know what is the two registers that you need to add them together. So these are from 16 to 20, from 21 to 25 are the two source registers that you need to add them together, right? So again, these encoding, these two 5 bits, okay? So hopefully this is clear. And the destination registers is located from 11, bits number 11 to 15. Here, right? And hopefully you you remember MIPS is big endian. So you know how to find these specific registers, right? And what else? Once you have that, so you need to give the value. So you need to locate these two specific registers, RS and RT, and send them to ALU. ALU basically does the add for you, right? Add these two numbers together. So you give two, again, each register is 32 bits, right? So you send these 32 bits to ALU and you get the result. And then you send back the result to register file, because write the content of this addition to the destination registers, right? So you need to write it back to appropriate write register, right? Specified here. In addition to this, so this is the data path, right? So again, each microarchitecture is constructed by data paths that we just discussed here. Like we had two data paths, right? One for incrementing PC, one for like adding these two registers and sending back the result, writing to the register. So this is everything that we need in terms of data paths, right? So there is nothing else that you need to do here. In addition to this, you need to send the right signal, control signal. What are those control signals? Again, going back to this slide, each of these, they have its own control signal, right? Meaning that, or maybe here is more obvious, meaning that you should specify whether you are writing to memory or you are reading from memory, okay? So each control signal needs to be specified appropriately. For example, the control signal for ALU is specifying obviously what function you want to execute. You know that ALU is a unit that implements different arithmetic operation. Specifically, it implements like all of these functions, right? Add, and or these are logic operation. Add, this is not used. A and not B, again, these two are logic operation. A minus B, and this is also reserved. So this is the ALU operation. We only need 3 bits because we have less than 8 operation needs to be implemented in this ALU. Obviously, if you're thinking again, like maybe we need more operations, then for a specific ISA that require ALU to implement more than 8, you obviously need more bits to specify the function. But like we have only these number of operations. So with 3 bits, we can encode all of these operations. So for add, we need to specify what operation we want ALU to execute. So we send 0, 1, 0 as a control signal to ALU. The interpretation of this is also somehow, you should be able to interpret this, but let me help you to understand what's going on here. Here you send A and B coming from here, right? So these are the input data. The control signal, you have 3 bits. The first 2 bits are sent here, okay? This is a max. The last bit, F2, are used here. This is an adder. This is a max here, right? Let's see. We have add here, A plus B. Okay, so 0, 1, 0. These two, F1 and F0 here. So this is corresponding to 2, meaning this will be selected. Let's see what comes here. Here you got A and maybe either B or not B, right? So this is NOR, right? Depending on what is F2. F2 in this case is 0. So B is, B is selected. So you get A, you get B here, and this 2 is selected. So A and B all the way down to Y. So you get A plus B. If you want something else, like let's say you've got A minus B, you should send this signal. Let's interpret this. So again, you have 2 here. So 2 here, the same here. A directly come here, okay? And then for B, we have 1, right? So we have 1, meaning not B. This is negation, right? So hopefully you can interpret this, each of these element logic gates. So not B, so meaning that A minus B, adding together, you get A minus B here. The same for logical operation. Logical operation, so you here have either 0 or 1. So you select either 0 or 1, okay? So if it is 0, meaning that this AND operation is selected. So this AND, like you have either A and B or A and not B. So A is always selected, and then depending on what is your F2, this upper bit, is either 0 or 1. So you get A, B for 0, or A not not B, right? For when the F2 is 1, right? So so now you should be able to interpret this. So here, like how many logic gates you need? So you need a AND, you need OR here because you also need to implement OR. You need one max here, one max, two max here, one adder here, and by add, like you already know that you can do a plus b or a minus b by negating b, and here is reserve, right? So so it's here. This one is not used. This is also reserved. Do you have any question about this interpretation? So hopefully this should be clear what's going on in the ALU. I presume you already are familiar with these logic gates in 211. So you can follow what I'm saying. But if not, if you need more clarification, please do let me know. So again, add, you need to send the value of two registers to ALU, A and B, send the right signal through ALU operation, because ALU implements multiple operations as you saw. So you need to tell ALU what operation I want to execute. And then in order to write the data back, you need to send one to register write. If register write is 0, it won't allow you to write anything into your register file. So in this instruction, you definitely need to write to the register file. This is specified by the semantic, right? So here you need to, whenever in the semantic of one instruction, you need general purpose register, you see general purpose register on the left-hand side of any particular part of the semantic, meaning that you are writing to general purpose register. You are writing to one of these registers. So you need to send one as a control signal to register file. Would otherwise do not allow you to write to register file. So again, emphasizing, what is microarchitecture? Is nothing, just a data path that we constructed and we made a sense out of it, plus the right control signal telling each element what they need to do, okay? Or what they expect to happen. So these control instruction and data path and control instruction needs to be coordinated in order to carry out the instruction. Would otherwise would not happen. And this happens through this combinational state update logic that that we discussed, right? So here we have some sort of again, to step back and think about this this other diagram that we had. Here, what you see, you have a bunch of combinational logic and some sequential logic that determines the state. So you already know these are the state elements, right? So these state elements should be familiar to you here as well, okay? So you have PC, you have memory, instruction memory, and register file, right? What are these elements that you see here? What are these 4 elements that you see here do not appear here, and why? It's very simple. I want a quick answer. What are those architectural state elements that existed, but you do not see it here, and why you do not see it here? Quick, I want answer.
You don't see the memory here.
That's right. Why we don't see the memory? And to clarify, we do see a memory, instruction memory, but we don't see a data memory, right? Why we don't see it here?
Is it because we are directly sending the ALU result back to write data and not, we don't need to store it as well?
That's absolutely correct. So look at the semantic. Nowhere in the semantic on the left side, we need to have access to the memory, right? So we add to the PC. Also, we like change the value of one of these general purpose registers. Nowhere here in the semantic you require to change the content of the data memory. So that's why you don't see it here, right? But again, this is not the complete microarchitecture. This is a part of the microarchitecture, MIPS microarchitecture, that only is associated to R-type instruction, right? All R types, you can implement it this way, right? And none of the R types in MIPS require you to write into the data memory. So you don't need it. But once we progress to other types of memory, you will see this new element, okay? So again, we incrementally add these architectural elements as we go and somehow interpret the semantic why we add this and like how the data path and contour signals look like, and pay a very special attention to this part of the lecture, right? These are like very common questions in exam, and like these are important part of the course that you need to know. Now, let's move on. Once we have the part of the microarchitecture implementing R-type instruction, let's do I-type. And you remember I-type, like instead of having two register as source operand, right? So you have the immediate, right? So you get one immediate in these 16 bits of the encoding, and these you also get two register, one as a source and one target, right? And these 6 bits specify the encoding of the function. Like for example, you have add I here, but you have other immediate or I-type instruction as well, okay? So here, for example, meaning that whatever you have in S1, you add 5 to it and write it back to S0. Okay, so hopefully it's clear. You already wrote program with this instruction, and like you are able to make sense out of the whole thing. So to review semantic, similar to R-type, we also need to add or increment PC. But also, we need to do one additional thing. We need to sign extend the immediate. So whatever you have in the immediate, you only have 16 bits. And in order to add to the source register, okay, how many bits you have here? 32, right? This immediate is only 16 bits, so you need to sign extend it to make it 32 bits. And we have discussed why we cannot have 32 bits immediate here, because it's impossible, right? We need some bits to specify the source target function, right? So we only, the designer of MIPS associated 16 bits to specify the immediate here in this case. So we need to sign extend it. So we obviously in the microarchitecture, we need some elements for this sign extension and add it to the content of this source register. And once you add them up, you move the data to this target register. Hopefully it is clear. The difference between R type and I type is that in R type, you have this to register to add whatever you want to do and whatever operation you want to do. But here you have one register plus one immediate. So you specify the second value through immediate in the instruction that you use. So that's essentially the difference between these two, but pretty much same. Okay. So here, how the microarchitecture looks like. As you guess, very similar to R-type. You have this part where you need to increment PC by 4. Here, again, similarly, we need to retrieve the instruction. Here, we have bunch of register that we need to specify, okay? And it is important because the places where these RS and RT are different from this encoding, right? Here, for example, this RS and RT, same place, but like the whole thing here are now specifying the immediate, and the functions previously was here, encoded here, now is encoded here, right? So where you can find these, each element now is slightly different, okay? So let's look at the different part, right? Okay, so here you obviously send bits number 16 to 32, these lower part of these 32 bits, these 16 bits at the end of the whole word, you sign extended. Imagine that you have a sign extended function here. You sign extended and send the result back to ALU, because again, here you need to, in terms of semantic, it was the same, exactly the same. We want to implement add, right? Previously, we had two registers to add them together, and both registers came from the register file. Now the second value comes from this sign extended version that you know how where it comes, these 16 bits in the encoded instruction. So you need to send this sign extended, send it to ALU. And then the rest is same. So whatever you get value added up, you need to write it back to the register. Again, like no memory, no data memory access. Obvious, like there is no memory access here. And you definitely need to write to this register file. So you send the right register file signal, right? So this reg write, you need to assign 1 to it. The same for ALU operation. And these are, again, to repeat that, this means that you need to send the right signal for each of these. Here, for example, you need 3 bits. These 3 bits needs to needs to be specified here by the right control signal, depending on what instruction it is. Okay, and then what else? Then the rest is pretty much the same, right? But here, again, like I mentioned, that we incrementally change the macro architecture. So previously, we had this macro architecture that this was wired here. Obviously, we cannot cut this. Like if we cut this, so now we are able to implement, to execute I type, but not R type. With this macro architecture, the way how you see it, you cannot execute the R type because this is cut. So we need to somehow wire back this to ALU. So we want to be able to execute both type of instructions. What are the options? Any idea? Do you have any suggestions? What could be the possible options? Give me two options. And why maybe one of them is better than the other. Talk about trade-off again. I want to make trade-off clear for you, like when it comes to designing a macro architecture. Think a few seconds and I want an answer. Think when, and you saw this already in 2.11, but also like here we had this example several times, right? When you have like, what do we have here? We have like two choices, right? Sometimes we need to wire this here. Sometimes we need to wire this here. But both of them needs to go to ALU, the second part. And ALU only like accept A and B and nothing more. So you have two inputs to ALU, right? But here, sometimes we need to wire this, sometimes we need to wire this. And this is an option, how we can put them together. So depending on the type of instruction, the right data goes to the right place. This is again about the data movement, right? We are constructing data paths, and as we add more instruction, we don't want to like cut part of the data path that was needed for other types of instruction. This is the thing that I'm discussing, right? So as we add the I type, we don't want to like mess with the R type. Still wants this macro architecture to implement R type. How we wire this to ALU?
You could just use a flip-flop.
Right, so you use the mux here. It's simple, right? So use mux, and then here you need to send the right signal to the mux, right? So is I type. So if I type, then you wire this, you select this input. If this is 0, meaning that this is not I type, On the other hand, this is R type, so this input would be selected and wired to ALU, right? So whenever you need a choice, MUX is your right architecture element, right logic gates in order to use, right? The same here. Okay, why we need to have this element, and this is going back to the encoding, right? So the encoding of R-type has 3 registers, right? So if I-type is selected, you need to select this one. If I-type is selected, you need to select this input, right? So this 4 bits, these 5 bits basically specify the register that you need to write the data to, right? No, sorry, these 11 to 15. So 11 to 15 determine the destination here, right? So this is 11 to 15. You need to you need it for the R type, right? And these 5 bits for the target register, right? So the 5 bit that determines where you want to write the result varies from like R type to I type. So you need to select the right 5 bits in order to find the register that you need to write to. And depending on the type of instruction, you can add MUX in order to locate it properly. So that's why we need a MUX here to select the right register for us to implement this. Was there any other way we could implement this without MUX? Like any other way that you could think of?
I think could you not just use a flip-flop to do it either? Like the multiplexer would be one way with the control signal to swap the two, but if you have different data, couldn't you just use the flip-flop? If, for example, if you're reading from read data 2 as opposed to sign extend, JK flip-flop will, I guess, and then you use that to control a like a gate or something.
How exactly? What do you?
I think it worked a lot better in my head.
So if you add a flip-flop to do what?
Add a flip-flop to control 2 different inputs. If you only ever want one of them out at once, so use a flip-flop to control if you want sign extend or read data 2 to go to the output. That way you don't ever have both, but you can have one. You can control the flip-flop similar to the multiplexer.
Where exactly we need to add the flip-flop? Yeah.
You would add them in the same locations as the multiplexers. I think in my head I just built multiplexers with flip-flops.
That's right. But again, like somehow you have a way to select either of these inputs, right? So essentially you get the same thing. What I'm asking, is there any other like totally different way that may result into totally different performance? Performance could be execution time, could be cost, whatever, right? But result in a totally different design at the microarchitecture. Any idea? How about adding one another ALU, right? Okay, ALU 2, okay? And then we get rid of this. We send here, and then we send this into here, okay? Does that work? But obviously we send the right wire back as well. So we use this ALU for R type. We use this ALU2 for I type, right? Because we essentially need the same operation. Like for R type, we need like add, we need and, logic and, right? The same thing for I type instruction. We need the same sort of functions. Like we replicate the same ALU like twice, instead of adding this max here. We make it clean, add it like depending on the instruction, we wire it to the right ALU. Does it make sense?
I have one question about that.
We need to change a little bit of this control signal, right? So we need to either add another control signal that determines when to use this, depending on what type it is, or add another bit here. There are multiple ways. But this is also another way of implementing the macro architecture. Can you reason about this performance stuff? Any idea about here? But this is obviously do the job for us, right? So we use 2 ALU. We don't have max here. We need to change a little bit of control signals, but essentially, like we get what we want. Do you see any problem here?
You have two ALU signals going to the same place. Is the biggest problem that I see. Yeah, you still have to figure out how to choose between the two output ALU signals.
Imagine that we will send the right control signal. So they find a way of wiring the right bits into here. Like, so for example, you could specify, depending on whether this is R type or I type, you send the right signal to allow any of these ALUs, either of these ALUs to be used, right? So imagine, I mean, this isn't, obviously you need some other elements here, but what I'm asking is that, imagine we do all of this. Obviously this implements whatever we want. This semantic implements both R type and I type either a slightly different control signal, some rewiring, some other elements that we need here, but essentially does the work for us. Like if you were asked which one do you prefer and reason about performance, how you approach this? Given that both implement the semantic of both R type and I type correctly, there is no incorrect implementation, right? Imagine that they implement the right, the correct semantic of either of these instructions. Which one do you prefer and why? These are important that I'm asking, so that's why I would like to ask you to think, and let's discuss it. Anyone wants to add? Are you listening, guys? If you are listening, why you are not answering? Bella, do you want to answer this? I mean, an incorrect answer, that's also fine. I want an answer. Can you verbally say what's the idea? What do you think? Which one you prefer and why? I mean, I'm asking about your preferences. There is nothing right or wrong. Either way is right. But I would like to hear why. Nothing? I'm asking about your preference. You should be able to discuss. I'm waiting. I'm not moving forward unless somebody answers. Do you understand my question? So we have two alternative design. Both design does the right thing, implement the right semantic of both type of instruction. Which design would you prefer? Why?
I would prefer the design with the multiplexers for implementing the instructions, just because it seems like it's simpler to control a single set of multiplexers with one input rather than controlling two different ALUs.
That's a good answer. Yeah, that's actually correct. Does have anybody else to add here? These are very, very important. This type of question you should expect to see in your exam. Like, I want an answer and I want an analytical discussion why that is the case.
I just thought of one more thing to add to what I said, and the based on like just the sizing constraints, it seems like an ALU would take up a lot more space on a small board than a couple of multiplexers.
Okay.
So implementing another ALU as opposed to two small multiplexers seems like a waste of space on a board. You can minimize it with two. You can minimize the space you use.
Okay, yeah, a space is a good thing, right? So yeah, ALU takes up more space than multiplexer, right? That's a very good thing, right? So you mentioned about like simplicity of the design and also a space. Is there anything else somebody wants to add beside Noah? Like both of his answers are correct and perfect. Is there anything else? Time efficiency, Stephen. Which one has better efficiency in terms of time? And why?
I would think maybe the ALU is quicker since it seems to take up more space.
But how it is related to time?
I'm not sure. I was just throwing out an idea.
Yeah, time also might. Yes, I mean in single cycle microarchitecture, maybe not, right? But in multi-cycle, since you have like two ALU and like I type and R type, you can make the data path totally independent. Maybe you can execute them, and if these two instructions are not interdependent in your program, and you can figure it out some way, you can execute them at the same time, right? You can execute them in parallel, right? And if that is the case, because like ALU does the thing and you have two ALUs, you can execute them at the same time, in the same cycle, like in the same thing, right? Assuming that you are able to execute things essentially in parallel. In single cycle, like you have one cycle, you do not have this flexibility. But in general, yes, if you had a more flexible design, you could gain some time efficiency if you add two ALUs, right? Because you have two resources now to do some calculation for you. Okay, that you can figure it out to increase the parallelism level and increase the time efficiency. Is there anything else that might influence and you would prefer one over another? There should be something else. The cost, Bella, can you elaborate how the cost matters here? Do you have a mic you want to use? Yeah, that's a very good point. The overall cost to build and implement these parts in mass production, right? Right. So you need to like implement two ALUs. You need to add two ALUs, and obviously, like if the cost of putting one ALU was X, now you need to pay 2X, right? And when you like consider the mass production, as you mentioned, this could be translated into $1 billion. The cost matters, right? All of these answers are perfect answer, actually. All of these are what I wanted to hear, right? So again, performance trade-off. If we add the second ALU, we may gain some efficiency in some specific design, depending if it's not single. Now we assume it's single cycle, but let's imagine that we have flexibility of doing things in parallel. But essentially, it affects cost, it affects time efficiency. As Noah said, it affects the space, right? So if you add ALU, means that like your board becomes larger, like you need part of the board to implement two ALUs. So there is a trade-off. A space is going on, and obviously you can have both design, but it comes with different trade-off. Another question: is there anything else here that you could implement differently that might potentially affect these, like cost, space, performance, simplicity? Simplicity of design is also something else that Noah mentioned. I liked it. Like simple design are important, elegant, simple as much as possible, but not simpler than to become trivial, right? Simplicity is very important. Is there any other part of this that you see that maybe you could change? It should be obvious. It's very obvious. Come on, look at the stuff you have, like 1, 2, 3, 4, 5, 6, 7, 8 elements. What else potentially you could change differently that affects these performance objectives?
Even with the same design on these types of schematics, wouldn't it also affect it depending on how you design the board? Like if someone poorly designs your circuit board in parts, it could take up more space to implement in the multiplex than the ALU if it's poorly done.
So what part exactly, what elements you can?
Really just the physical elements. Like everything would still connect to the same parts, but on the design of the circuit board, if they gave them more space between the connections and didn't fit things on the actual hardware properly, I feel like it would affect the space part of it and possibly even the time.
Right. So what you are suggesting, maybe like we could improve like memory itself, right? Maybe we could, since we need to have access to the memory, like anyway here to instruction memory, right? If we like improve this memory, we gain efficiency, right? So we can execute the things like faster if we make the memory access faster, right? Is that what you're suggesting?
That could easily be part of it. So yeah, I'll just go with that.
Yeah, and also like, for example, registers as well, maybe ALU, right? You saw the design, a design of a ALU, right? Here, but this could be implemented differently, right? Sorry, I forgot your name, Bella, right? Did you answer or somebody else?
It was me.
Thanks. That's certainly an answer. But is there anything like in terms of like the example that we discussed here, adding a ALU? Is there any other elements that you could remove or add here that give you the same semantic but different performance? Any guess that should be fine.
Could you not come up with a way to make the ALU also do the process counter function, the +4 to the process counter?
That's right. We have one adder here, like part of ALU implements also add, right? So look at this thing, right? So you have adder essentially here as well, right? So you add things. So you could give it PC here B4, right? So you could remove these, right? So one possible way is to get rid of this. You could wire this here, okay? And then 4 here. Obviously, you need a element here, max. Now selecting between 3, right? This one, and 4, depending on where the input come from, and send the right signal. Here, instead of like, since you have 3 inputs, like you cannot have 1 bit, so you need 2 bits, right, to decide which one, right? Here, you also need a max here to select between 2. With 1 bit, you can figure it out. And then you got like, you also need to like add this wiring here. And then you got this done, right? You remove this adder. This obviously does the thing, but as we discussed, like it influences performance, and it has some consequences if you think about it. So you remember we needed to do this together in the same cycle, right? We could implement this using the same ALU, adding some elements, saving some like cost with respect to other, changing some of these control signals. But this could complicate things because, again, here we have 2 separate data paths. Since these are 2 separate data paths, we can safely do this thing and this thing at the same time, right? And you remember the discussion about this semantic. So this needs to be written at the right time. So when we fetch the instruction, I mean, if this will be written quickly, once we comes to the fetching the instruction, this could mess with the semantic if we read this after this has been incremented, right? Then we read, instead of reading the current instruction, we will read the next instruction, which is obviously not what we want to do. So this write signal here, and also like this part, needs to be coordinated in a right way in order to execute things correctly, semantically correct. So adding this extra overhead of coordinating this thing, and like definitely since we have one resources at the time, this ALU cannot do both things right at the same time. So like there would be a need for coordinating these things, and it adds some overhead for this. So obviously we could, but again, performance trade-off, right? Performance trade-off is super important, as I discussed, and these are essential part of any microarchitecture design that you need to remember when it comes to designing microarchitecture, right? Okay, give me a few more minutes so I can finish this. Clear all drawing. Okay. This is also very similar microarchitecture for LCT. LCT like add this add, if you remember, you could have it with 2 register, right? Or having immediate, right? Depending on how you want it, depending on like this 1 bit. Like if this was 1, you should use this as, you should sign extend this and use it as the second operand. Would otherwise you had this second register where you could add the value of these 2 register and write the data back to the destination register, right? So you had an operand, you had destination register, you had source register, and depending on this bit, you either, if it was 1, you had immediate, or you had the second operand that you could read from this register file. So you have the same element. You have ALU. You have some control signal that comes from finite state machine that we will discuss later on. But essentially, very similar microarchitecture with the slight difference, and this difference comes from this particular encoding. And like the encoding of LC3 is like the number of bits are smaller, 16 instead of 32 bits. These register files are smaller, 16 bits. But like if you compare this microarchitecture, this is again microarchitecture for implementing add, is very similar to this, right? So you had some multiplexer here to choose from, either the second register or the immediate. And you have a bunch of other stuff to implement the right instruction for you. So again, contrasting these 2 different microarchitecture is useful. Maybe let me see how much time do I need to explain this. Maybe let's do this next week. Let's just stop here, so we can go into the detail of data path for data movement instruction. Data movement instruction. So far, what we discussed was R type and I type. Again, to recap, we started by this simple R-type microarchitecture, and then we add some new elements to enable us to do both R-type and I-type. Next, the other important category of MIPS instruction are data movement. Essentially, is load word and store word, which you will see. You see now a new element that you need to add definitely in this microarchitecture, which is data memory. And somehow you need to wire things in order to implement either load word. Load word, you need to locate the right memory address and load the content of it back to the register file, to the right register. A store word, you need to again find the right address and write to the memory the content that you get out of this ALU, right? So you need to do some wiring here in order to give it the right address and give it the right data, right? And also sending the right control signal, depending on whether you have load word or store word, you need to set this correctly, like memory write for a store word, memory read for load word. So by sending the right, by constructing the right data path to enable this, and sending the right control signal, next time we add this new type of instructions, that obviously here you see totally different semantic. Here you have effective address that you need to calculate, and here like you change the content of a GPR, but also you have a new thing. You have access to the memory. Here you read from the memory. Here you write to the memory. So the memory access, you see on the left part of one of these instruction, one of these part of the instruction, right? So you need to figure out the right wiring in order to enable you to send the right data and send the right control signal in order to implement the right instruction correctly. Again, this is translating into combinational state-update logic. This all the whole microarchitecture is wiring some combinational logic gates with some memory that does that implements the instructions, right? This all of this microarchitecture that we discussed is nothing but just a variation of this single cycle machine, a combination of combinational logic plus a sequential logic, which basically store the state of the machine. Obviously, when we move to multi-cycle, this looks like differently, but all the single cycle microarchitecture that we'll discuss at the abstract level, if you think about it, has obviously some elements. Like you have multiple like a state element, you have multiple combination logic, but at abstract level, you can abstract the whole thing into this this type of combination of combination logic and sequential logic. Let's stop here. Few things. Make sure that you submit the quiz on time. There will be absolutely no extension, no excuse. You have enough time. Make sure to understand you have limited time. Once you start, you have 2 hours to answer it. You don't need to like write 2 pages for this. Be brief, but communicate the right, analysis. Either you could use formula, some written English, however you prefer, but communicate the correct answer so we can understand it. And see you guys next week with continuation of the microarchitecture. You should also expect to get the next homework probably over weekend. And after that, you should be ready to have the midterm. And again, for midterm, like I don't want to stress you out. As long as you listen to the lecture and you followed what I'm saying and you understand it, if you did not, like ask your question in the lectures or post your question in Piazza so we can answer it, you should be fine. There is nothing that, but also I would suggest reading the textbook, these 2 important sections about programming and microarchitecture. If you do this, you should be fine. I don't see any reason why you cannot get the full grades. Thank you. I will stay here for a few minutes if you have any question.
Thank you, Professor.
Sure.